it is naked. So bare, naked. Bare means this does not have a reactor does not have reflector. So bare reactor and reflected reactor is uh, uh, in comparison. So bare without close, reflected we have reflector. So uh, I already mentioned when in nuclear engineering, sometimes we call bare reactor as Godiva, right? Now we will deal with reflected reactor. Now, reflector. Uh, this is not a mirror. This is not a mirror. So this is like a water jacket. Water jacket. So uh, in the water jacket we have lots of water molecules. So when the neutron uh, submit when the neutron pass through the water jacket, then it undergoes a lot of scattering interaction with water or hydrogen or oxygen inside of the water. So during the scattering process, some neutron scattered back, some neutron scattered back. So it is not a mirror. So, but we call it reflector. But it is kind of a water jacket, so that when neutron leaked from the reactor core, it escaped from the reactor, and then in they arrived in the reflector zone, and they undergo um, scattering interaction with the water molecules, and then some more neutrons scattered back to the reactor. Scattered back to the reactor. So this is a reflector, not a mirror, not a mirror. So when we have a reflector, we the neutron leakage is reduced. Okay, neutron leakage is reduced. That means we can use neutron for we can use more neutron for fission because the leakage is reduced. So in our terminology, we can say neutron economy is improved. Okay, neutron economy is improved because that means we don't no, we reduce the neutron leakage, and we use more neutron for nuclear fission. For sometimes uh, uh, we can use more neutron to convert fertile material to fissile material. Okay, anyway, there is a neutron economy. Now, let's look at the governing equation. Uh, we consider the spherical reactor, spherical. Now, for the core region and reflector region, for the core region, reactor equation. For the reflector, diffusion equation. Because in the reflector, there is no fuel. Okay, no fuel. So reflector only moderator zone. So this is just the media. So reactor equation, Laplacian phi c plus b square phi c equals 0. This is a reactor equation, and this is we learned in chapter 6. But for the reflector, Laplacian square phi r plus 1 over L r squared phi r. This is diffusion. This was the diffusion equation. We learned it at chapter 5, right? So the governing equation for core and reflector is reactor equation and diffusion equation. And nextly, we know the solution for the core. Phi c equals a sine br divided by r. And reflector, a different a, so it's a prime. expansion minus r per lt divided by r. So this is the general solution. Now we have the governing equation and general solution. Now, so we need to have a boundary condition. So actually, this is not a boundary condition. This is an interface condition between core and reflector. The core and we have two boundary conditions. First one, phi c r and phi r at r should be the same. So this means when we calculate the neutron flux from the core and then substitute large r in the place of small r, and then we have the value. And also we can calculate the flux from the reflector region and then substitute large r in the place of small r. Then these two values should be the same. That is continuous in mathematics. This is just a continuous condition. 연속 조건, continuous condition. The next one, JCR times N, JRR times N. So now it is written, JC is written in boldface, and N is written in boldface again. So these two values are vector. So inner product of these two vectors become scalar. Anyway, JC is from the definition of current minus d phi dx or d phi dr, right? So that means the second boundary condition, second interface condition is the first boundary condition, phi cr equal phi r, is a continuous condition. So flux value should be the same. The second equation is minus d phi dr and minus d phi dr is the same. So that means the differentiated value of phi at location r is the same. Okay, so this is in mathematics, when we learn this, is differentiable. Okay, so the first interface condition is continuous condition, and second interface condition is a differential condition. So the value of phi, the differentiated phi calculated from the core, and the value calculated from the reflector should be the same. That means differentiable. So this should be the same. So first equation is continuous condition, and second equation is differentiable condition. So if you are not accustomed to this kind of expression, continuous condition and differentiable condition, you have to look up mathematical handbook. Okay. Now, when we apply interface condition, a sine br divided by r and a prime exponential minus r over dr divided by r. So 6.90, that is continuous condition. And for for J, so we should differentiate the flux. So this is multiplied term. So we have two terms. So when we differentiate the general solution and then substitute large r in place of small r, then we get 6.91. Okay, 6.91. And we have 6.90 and 6.91. Now, instead of solving for a and a prime, that is quite meaningless. A and a prime is meaningless in some sense. Why? because we cannot get value a and a prime from this equation. We get the value from power. Okay, so that means we would better uh, not concentrate on a or a prime. So what the things we can do is we divided 6.91 with 6.90. So we divide 6.91 with 6.90. Left hand side, left hand side, right hand side, right hand side. Then we get next equation. And a is cancelled out, a prime is cancelled out. Now, this is the equation. So the question is, we know D, we know B, we know R. So we know also B. So, but what we BR we have to calculate. We have to calculate. So when we rearrange this thing, we have to calculate R. We have to calculate R. So let's look at again the equation. PR cotangent BR minus 1 equals dr minus dr divided by dc and r divided by l plus 1. Now, this equation, left hand side is trigonometric equation because we have cotangent, and right hand side is algebraic equation. 좌변은 삼각함수, 우변은 산술식. So left hand side is trigonometric equation and right hand side is algebraic equation, and we have to solve for R. Right. Did we experience this kind of thing previously? No, we didn't. Right. Trigonometric and algebraic. So we cannot solve this equation by analytically. So what else we can do is we can solve it by graphically. So let's define y1 equals PR cotangent BR minus 1, and define y2 minus dr over dc multiplied by r over the rr plus 1. So we separate left hand side, right hand side, and plot on the figure, on the same figure, and let's investigate where the left hand side and right hand side has the same value, like this. So before we proceed, the axis, horizontal axis is BR, B multiplied by R. And as you see from this arrow, left hand side is cotangent curve. So around pi, the value goes to infinite or minus infinite. So we have this kind of shape again, same pattern again and again. Now, dr over right hand side is just line, okay? Because we have one r, so one r and it's constant. So the right hand side is the straight line. Now, left hand side and right hand side meet at position root, R-O-O-T. Do you see the root? So the new BR value is a little bit smaller than pi. Okay, so if it were a Bayer reactor, BR should be phi. BR should be pi. But now, with the reflected reactor, the value of BR is lower than pi. That means the critical radius is smaller than the critical radius of bare reactor. Okay, so uh, again, uh, if it were a bare reactor, PR should be pi. But in this graph, the root comes just before pi. So PR of the reflected reactor is less than pi. That means the reflected reactor requires smaller critical radius. Okay, that is important finding. Anyway, this kind of equation, we call it transcendental equation, 초월함수, transcendental equation. So as to the transcendental equation, we cannot solve it algebraically. So we have to solve it by graphical means. Or we can solve it by computer. But anyway, so when we don't have computer, we have to solve it by plotting graph. A, again, from the power level. Okay, so in the reflector region, flux, we don't have to know, because in the reflector region, they don't produce power. So we need phi c, core flux. Okay, and the value of A can be calculated from the power. So power equals ER, so the ER again, energy released per fission, and multiplied by number of fission. Number of fission is sigma F, and integrate phi c all over the sphere. Okay. From there, we get A value. Then substitute A value to the original equation, and then we get A prime. So we get phi c and phi r. Now, before we go to the next step, let's look at the flux shape. So there is a fast flux F phi 1, and the core region and reflector region is shown. And there is a summer flux for the bare reactor and summer flux for the reflected reactor. Okay, so first thing we can see is just this one. For the bare reactor and reflected reactor, the fast flux phi 1 is the same. So that means reflector affect only the thermal neutron flux, not fast neutron. Is it understandable? Right. Fast neutron doesn't undergo scattering interaction very much in the reflector, so it just leaked. But the thermal reactor undergoes scattering interaction in the thermal reactor, reflector region. So the first thing, even though we have the reflector, the fast flux is still the same as the bare reactor. That is one thing. Second thing, there is thermal flux for the bare reactor. Let's compare the thermal flux for the bare reactor and thermal flux for the reflected reactor. So we have a hump in the thermal flux in the reflector region. So because there is the number of neutron increase because there is a backscattered neutrons. So the second thing we can see is there is a difference of thermal flux for the bare reactor and reflected reactor. And third thing, And the difference is in the reflector region. In the center region, the thermal flux is the same. Only in the reflected region, near reflected region, the flux is varying. That is third thing. And fourth thing is when we have reflector, the flux shape is more flat. So thermal reactor this way, but reflected reactor is this way. So it is more flat. So as a nuclear engineer, in order to produce more power, we would like to have flat flux shape. So that is our idea. So reflected, this means reflector helps first neutron economy. It catches some leaked neutron. So it enhances the neutron economy. Second thing is it flattens flux. It flattens the flux. 플럭스를 flatten, 평평하게 해준다 이거야. 그게 장점이다 이거지. Okay, so this is the reflector. I think okay, so we have an example, but it takes so much time to solve the example, so I will leave it to the next lecture. So let's call it a day. So practice. Second thing, read the textbook, please. Okay, bye-bye.